Hi guys, day 2 of circles. We've got some more theorems, we've got some more practice problems, and so we're just going to jump right into it. If you don't remember some things from the other day, feel free to go back to the last video and look at those examples and those vocab words. All right, so this first theorem that we're going to talk about today says in the same circle or in congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. So that means if I have one circle, this circle that I have over here to the right, the arcs AB and BC are congruent if and only if their corresponding chords are congruent. So that means the segment or the chord AB is congruent to the segment chord BC. Same thing if we went the other way around. So those arcs are congruent. I'm going to put little congruent marks. If I went the other way, if I told you AB and BC were congruent, then I could assume that arc BC and arc AB were also congruent. Okay, so let's use that to do a few examples. The first one says find measure of arc AB. So that's this part right here. I know this is kind of hard to read because it's small and not super well labeled, so just trust me on this. It looks like it's labeled like the chord CD is 16 and the chord AB is also 16. So since those chords are congruent, then we're going to say that their arcs are congruent. Well, if the arc CD is 108, then that means the arc AB is also 108. Oh, that was lucky. I didn't have to do any math. All right, that's not true for the next one. As you can see, we've got some expressions. So it says circle J and circle K are congruent. So that means that I can use the same knowledge that I just learned about in this theorem. Arcs MN and PQ are congruent, as they've got a little congruent mark on them. So we need to find out what PQ is. Well, if the arcs are congruent in these congruent circles, then I get to say that their chords are also congruent. So I'm going to set up an equation. I'm going to say 2x plus 1 is equal to 3x minus 7. I'm going to minus 2x from both sides to get x. I'm going to add 7 to both sides to get 8. Oh, nice. X equals 8. But before I move on, it says find PQ, so I got to plug that back in to the PQ guy and figure out what it is. So PQ is this, 3x minus 7. 3x minus 7, x is 8. 3 times 8 is 24. 24 minus 7 is 17. So that is my answer right there. Cool, and then the last example for this theorem says that we're given circle P is congruent to circle Q, so I'm going to use the same concept I did before. And it says that RS is 3x, and it's across from an arc that's labeled 155. And then it says TU is 7x minus 44. And we don't know what the length of its arc is. Whoa. But I do know that its major arc, I don't know its minor arc, but I know its major arc is 205. What should both of these arcs added together be? 360. So if I do 360 minus 205, I'm going to see if it's the same thing as that 155, and if it is, then I get to set my chords equal to each other. All right, if I start subtracting, carry that 1 over, oh, I do get 155. Nice. So they are congruent. So I'm going to set them equal to each other. I'm going to say 3x equals 7x minus 44. And minus that 7x from both sides, negative 4x equals negative 44. Divide by negative 4, x equals 11. How much would that chord be? I don't know if it asked us. You could plug it into either one. I would probably plug it into that 3x because that's going to be a lot easier than 7x and the minus 44. But the chord would actually be 33. I don't know if it asked that, but it's good to practice. All right, move on. That was the first theorem. Now we're on the second one. This one says, in the same circle, or again in two congruent circles, two chords are congruent if and only if they are equidistant from the center. Equidistant from the center means that AB is congruent to CD if and only if EF is congruent to GF. Or no, GE, sorry. EF, and for consistency, I'll say EG. Yep. So those two itty bitty segments, I know they're really small, but if those are the same, then the chords are also congruent. Same, likewise, if I told you that the little segments that go from the center to the chord, E, G, and EF, if I told you those were congruent, then we could assume that the chords are also congruent. So you can go vice versa. All right, a few examples with this one. In circle H, PQ is equal to 3x minus 4, and RS is equal to 14. I'm not going to label those, but you can label them if you want. And then it tells us that HT is 8, and it tells us HU is also 8. Ooh, those are equidistant, those are congruent, so I get to set my chords equal to each other. 3x minus 4 is equal to 14. Add 4 to both sides, divide by 3, x equals 6. It just said find 6, so I'm going to keep moving. In circle A, WX is equal to XY, which is equal to 22. WX, XY. So that's like this whole segment right there. That's 22, that's 22. If the chords are congruent, then what does that mean about the distance from the chord to the center? Those are equidistant, those are congruent, so I'm going to set 5x equal to 3x plus 4. Minus 3x from both sides, divide by 2, x equals 2. Oh, before I move on, it says, what is AB? Let me erase some of this stuff so I can see where AB is. Okay, AB is right here. AB is going to be 5 times x. If x is 2, then AB is 10. I don't have any units, so I'm just going to leave it as 10. Questions so far? Pause if you need to, go back if you need to. I'm going to keep rolling. I think this is the third theorem we're going to talk about today. It says, in a circle, a diameter is perpendicular, or a right angle, to a chord if and only if it bisects the chord and bisects the arc. Okay, so the diameter is perpendicular to a chord. So the diameter here that I'm tracing in red is only perpendicular to the chord DF in blue if the diameter bisects the chord and bisects the arc. That means that the diameter needs to put DF into two congruent pieces. So that means that that chord is cut in two congruent pieces. DE is congruent to EF. And also the chord is in two pieces that are congruent. So DG, and I'm going to use an arc over that, is congruent to FG. Again, put an arc over that because I'm now talking about arcs. Vice versa, if I knew that the chord was bisected and I knew that the arc was bisected, then I could say that the diameter was perpendicular to that chord. So again, these are all if and only ifs. You can go both ways. Remember our thumbs? We could cross our hands and it would still be a true statement. I'm doing it here, but you can't see it because it's not that kind of video. So hopefully you're doing it at home too, or ignoring that. Okay, moving on. In circle S, it says measure of PQR is equal to 98. So PQR, this whole arc right here, is equal to 98. Find measure of PQ. Well, it tells us that QT and PR are perpendicular. I've got a little perpendicular mark, which means that my arcs are split into two congruent pieces. It's bisected. So that means I can think of it as 98 divided by 2, and that's going to be 49. Oh, that looks like 99. Let me fix that. 49. So that's how much measure of arc PQ is. Next example. This one's a little challenging. It says in circle R, find measure of TV. Round to the nearest hundredth. So since it says round, we're going to use decimals. If I don't say round, don't use a decimal. Okay, we know that the distance from the center to the chord is 6, and we know the distance from the chord to the end of the circle is 5. How much is the total radius? Yep, it's 11. So anywhere I draw on the circle, if I go from the center to the outside, it's 11 units, okay? I drew it purposely from R to T because I want a little right triangle. I want this right triangle right there, and I'm going to draw that outside my circle. A little bit bigger. Oh, that's ugly. Let's try again. I know that from R to T, the radius is 11, and I know from the center to the chord is 6. So down here is 6. We don't know what half of the chord is. That's what we want to find. We want to find the whole chord, but if I find the half first, then I can multiply that by 2 and find all of it. Again, we're trying to find this right here. And so if I can find the half that's the green that overlaps with the red, then I'll just multiply x times 2 and find my whole answer. This is nice because now we can use our friend the Pythagorean theorem in order to solve. X squared plus 6 squared equals 11 squared. X squared plus 36 equals 121. Minus 36 from both sides, I get 85. Square root both sides, I get x equals radical 85. Now, I don't want just one of them, I want the whole thing, so I'm going to multiply that by 2. So I'm going to do 2 times radical 85 to get all of TV. This is technically just TS. And if I want TV, then I'm going to have to multiply this by 2. Okay, you can look at your picture to kind of see that. Or you can add it to itself twice, but I'd rather multiply. It's the same operation. That becomes 2 radical 85, and again, I said round to the nearest hundredth, so when I put that in my calculator, I got out about 18.45. We don't know what the units on here is. We don't know if it's inches or feet or whatever, so we're going to leave it like that. Okay, got a couple more examples like this. This one is very similar. We're still doing a triangle-like thing. It says find the value of y. We know this time, though, that the chord is 11 and 11, which means that that whole chord is 22. We don't know what y is, but we do know the radius. What's the radius of the circle? 15, good. We are going to use our little right triangle right here. We know this is 11. I know that's 15. And I'm going to use this as y. So again, our friend the Pythagorean theorem. 11 squared plus y squared equals 15 squared. 121 plus y squared equals 225. Y squared is going to equal 104. Square root. And y equals radical 104, or approximately, I think we're still on the rounding direction, so approximately 10.2. My stylus is being really funny today, guys. I'm sorry. 102. There we go. That's my value of y. Okay, this one says circles A and B are congruent. CD is a chord on both circles. So we've got a little bit of like a Venn diagram thing here. A, B together is 8. And then CD together is 6. Ooh, that's ugly. 6. Okay, so we want to figure out what the radius is. Well, I can't just split AB in half and get the radius because that doesn't go all the way to the edge of the circle. There's a little bit of an overlap, so we can't just divide it off. However, if we I'm just erasing this so I can look at the circle. Again, if I cut it in half, it would stop here, and I need it to go all the way here, so it wouldn't be exactly right in the middle. I can think of this as a triangle, though. I can go from AD, D to the middle, and then that middle to A. We know that half of AB is what? Well, it's going to be 4. Half of 8 is 4. What about CD? What's half of CD, or 6? 3. Okay, I've got a nice little right triangle. Guess what we're going to do? You got it, Pythagorean theorem. 3 squared plus 4 squared equals, I don't care what variable you use there, squared. 9 plus 16 equals x squared. Add those two together. 25 equals x squared. Square root both sides. 5 equals x. That's how long the radius is. That takes into consideration, if I go from A to D, that goes all the way to the edge of the circle from the center. It doesn't split it in half, it goes a little bit all the way to the edge. So both radiuses in these congruent circles is 5. All right, we got a couple definitions and 2 more theorems. So hang in there, guys, you're doing great. Definition. If all of the polygons vertices lie on the circle, then a polygon is said to be inscribed in the circle. I know I was using inscribed earlier, and I kind of glossed over it. Inscribed means that it's inside. It's completely inside of the circle, and all of its vertices are on the circle. The circle is circumscribed about the polygon. That means it's on the inside of. So if I say circumscribed, it's not on the inside of. The circle is on the outside of the polygon. The polygon's now on the inside. The circle is on the outside. So I'm going to say outside here. So depending on what the directions say, the first word, it says if a polygon is inscribed, then the polygon is inside the circle. And then it says the circle is circumscribed around the polygon, the circle is outside the polygon. So if you kind of interchange those words, it makes a little bit more sense. So the first of the last theorems that we're going to talk about is if a right triangle is inscribed or inside a circle, then its hypotenuse is a diameter of the circle. It's the diameter. It goes all the way from one end point to the other, and it goes right through the center with a right angle in there. Another way of thinking about this is if a triangle is inscribed in a semicircle, then it is a right triangle. So if you have, it's one side is like the base of that semicircle, and then the third point is just somewhere on that circle, it has to be a right triangle. It has to make a right angle. Okay, so I've got 2 different circles and a couple examples with each one. In both of these cases, we have a diameter. WX is the diameter in the first one, RT is the diameter in the second one. We have to know that these are right triangles. So angle Y is a right angle, and angle S is also a right angle, so that's going to help us know what's going on. If you think you know this, I would pause this video and try it on your own. If you're not sure, hang with me. I got you. In order to figure out what x is, we can add up all of the angles in this triangle and solve for x. So we know that we've got a 90-degree angle, we have an angle called x, and then we have one called x plus 12. And those 3 together should make 180. I have 2 x's, and I've got 102. Oh god, that's ugly. There we go, that's a little better. Only a little bit. Minus your 102 from both sides, divide by 2, x is going to equal 39. So little x is 39. And I'm going to throw a degree because there's actually an angle called little x, and it's a full degree. So 39 degrees is angle x or little x that we solve for. How do I find measure of angle W? Easy. If I have x, and I know x is 39, I'm going to do 39 plus 12. 39 plus 12 is going to be 51. And if we wanted to check our work, you could do 39 plus 51 plus 90, and does that equal 180? Yes, it does. All right, next one. Again, I've got my right triangle that's inscribed in a circle. The circle is circumscribed about the triangle. Again, I've got a right angle, so I'm going to add up all my angles and set them equal to 180. 2x plus 4x minus 6 plus 90 equals 180. 6x plus 84 equals 180. 6x equals 96. Divide by 6, x equals 31. Yep. Nope. Nope, I looked too far ahead. 16. My fault. 16. X equals 16, and then it asks for measure of angle T. I can plug in 16 for x to get t. So I'm going to do 4 times 16 minus 6, and that's going to be 58 degrees. Again, you can plug and chug if you want to check. Whew, all right, one last theorem. This one says a quadrilateral can be inscribed or inside a circle if and only if its opposite angles are supplementary. Ooh, we haven't talked about supplementary for a second. What does that mean? Yep, it adds to 180, sums to 180. Okay, so opposite angles. What counts as opposite angles? A and C. Yes, they're across from each other. So measure of angle C and measure of angle A go together. And then that means the other two go together, B and D, because they are also opposite across from each other. Measure of angle B plus measure of angle D. So we're going to use that concept for these last couple examples. So the first one says solve for x and y. So which two get to go together? Y goes with 87. Now remember, they're not congruent, they're supplementary. So y plus 87 equals 180 minus 87 from both sides, so y equals 93. Okay, and then let's do x, 2x and 100, so 2x plus 100 equals 180, 2x equals 80, x equals 40. Awesome. All right, let's try the next one. All right, which two go together? We'll do 2x and x plus 18. Okay, that's nice. 2x plus x plus 18 equals 180. 3x plus 18 equals 180. 3x equals 162. And x equals 54. That's not bad. Before we go on, it does ask what angle W is. So to find angle W, we just do 54 plus 18. And 54 plus 18 equals 72. Okay, and then we have to do the other one. 3y minus 7. Oh, that was a terrible circle. 3y minus 7, 3y plus 1. Those guys are also supplementary. 3y minus 7 plus 3y plus 1 equals 180. 6y minus 6 equals 180. 6y equals 186. Y equals, this is the 31 I was talking about. And to find angle x, oh, where did angle x go? Let me erase some of this stuff. Okay, angle x is at 3y minus 7. So I'm going to do 3 times 31 minus 7. When I work that out, I get 86. And you could plug in to find z and y and then make sure all of those guys add up to 360. But this work is correct with all our supplementary angles. The opposite angles are supplementary. Okay, and then the last example we have to do. This one's a fun one. This gives us some algebra practice. It says RSTU is inscribed in circle P. Solve for x and y. Then find the measures of each angle. So we got to find our opposite ones. So I've got angle S and angle U. 12x plus 21y equals 180. Ooh. Huh. And then let's do our other ones, T and R. 8x plus 29y equals 180. Why didn't I solve the blue and then go solve the green? Why did I write both of them? Good, I cannot solve either of them independently because they have two variables. We actually have to do a systems of equations here because we need to get common, we can't solve like one equation with two different variables. You need two equations. So we're going to do some elimination. So I'm going to get the x's, I think, to cancel out. So I think if I multiply this first equation by -2, that will make us have -24x. And if I multiply the bottom equation by positive 3, that will give us a positive 24x. Okay, those will cancel out. You could have thought of a bunch of different ways to solve this. I just think this is the simplest. So feel free to try a different method on your own and then come back and check to see if you got the right answer. So I'm going to keep solving. I've got negative 24x. I've got minus 42y equals negative 360. And then I've got positive 24x and positive 87y and positive 540. Together, the x's cancel. I get 45y equals 180, and then I divide by 45, and I get y equals 4. In order to solve, you just put that y into any of the other equations. So I'm going to do 12x plus 21 times 4 equals 180. The one I did is not more correct than the other one. I just felt like doing this one. You could have done the green equation. You could have plugged it in even to the orange one after you changed it. Does not matter. 12x plus 84 equals 180. We're going to minus 84 from both sides. I get 96. 12x equals 96. Divide by 12, and then x equals 8. And that's it. Oh, no, wait, it says find the measure of each angle. Let's do that real fast. Just some multiplying, so I'm not going to show the workout, but for angle S, I'm doing 12 times 8, which is 96 degrees. For angle T, I'm doing 8 times x, which is 8. 8 times 8 is 64. Angle U is 21 times y, which is 4. 21 times 4 is 84. And then angle R is 29 times y, or 29 times 4, which is 116. Now, if you wanted to double check your work, you could add them all up. 116 plus 96 plus 64 plus 84 equals 360. The end. Reach out if you need any help. Good luck on your homework. Good luck practicing circles and all these theorems and all these new things you know about them. Have a good rest of your day, guys.